Okay, so thank you to the organizers for giving me this opportunity to speak at the 16th CNTA. I will be talking about exponential relations among algebraic integer conjugates today. So first, I have the outline. So what I'm going to be doing is, well, you see the title, so let's make the title clear for everyone. So I'm going to be explaining what I mean by algebraic integer conjugates, and then what I mean by the exponential relations among them. And then before we proceed to any results, I want to give some of the motivation we had that I want to illustrate. And then I'm going to be presenting the main results. We have two main theorems. And in the first theorem, we have two characterizations. So I'm going to be also illustrating some examples, and then we're going to see theorem 2. Okay, so first, algebraic integer conjugates. So here is the setup. So we have k and d, which are natural numbers. K is at least 1, and d is at least 2. And k is going to be always strictly less than d for us. And we have these algebraic integers, alpha 0, alpha 1 to alpha d minus 1 of degree d. These are going to be the Galois conjugates that I'm going to be talking about throughout the talk. And we also assume that they are not roots of unity. So we also have this ordering of the roots of Galois conjugates. And it is an ordering in terms of modulus, and it's a non-increasing ordering, or if you want, they're in decreasing order, but it's not strictly decreasing. So what do I mean by exponential relations? So this is the inequality that we mean when we say that. So you see here the exponents are on top of the Galois conjugates moduli. And we are looking at this type of product, and we want to look at the solutions that are the k tuples. So by the solutions, I mean the C1 to Ck that satisfy this type of inequality with the alpha i's as in the setup here. And here, all the Ci's are non-negative real numbers. So what we wonder is, okay, we want to look at the solution set of all solutions. And we're going to be also asking this question, what is the shape of the set of solutions in terms of geometric shape? And well, second question is, when do we have the strict inequality if we strict ourselves to greater or equal to 1? Or equivalently, when do we have the equality with 1? Answering one of these will also characterize the other one. And lastly, what do I even mean by when? So we're going to get to that as well. Well, here, maybe I can move this. Yep. Okay, so the question is, why do we care about this? I want to put this on the side, but okay. So why do we care? Here I have this inequality, and it goes up to k, and we have so many terms in the product. So let's go a bit simpler and look at this one. So here I just have k equals 1, so I just have a C1. And the fact is, in this setup, we always have this inequality, right, with d minus 1. And this works because of the ordering you have, actually, because, you know, alpha 1 is greater than or equal to the modulus of alpha 2, and so on. So what you could do is, if you just drop this power by 1, and then replace the alpha 1 with alpha 2, which would be smaller, and then go down to alpha d minus 1, and it's going to be like you have just the product of the roots. Again, I'm thinking of a polynomial here. And then that's always going to be greater than or equal to 1, because the polynomial is over z. And then here is a sneak peek, right? So this was just to look at it in a simpler way. But if you have up to k, and you have C1 to Ck, then we expect, we're going to see that then the sum is at most d minus 1. So here it's only C1, and we see, well, C1 is at most d minus 1. It says d minus 1. Let's see a more concrete example. So I kept saying roots, well, because I'm thinking of a polynomial. Consider this polynomial x squared minus x minus 1. Does anybody recognize this polynomial as a special polynomial? What type of special polynomial could this be?
Fibonacci.
Yes, that is the correct answer. At least the answer that I was expecting. Thank you. So this is the characteristic polynomial of the Fibonacci sequence, which is a very special sequence. Everybody knows about it. And here, I'm going to be looking at this, through the lens of our setup. Here we have d equals 2, and we're going to be looking at k equals 1 again. We actually know the roots of this polynomial. Can anybody tell me the roots of this polynomial? Yes?
Golden ratio.
Yeah, there's a golden ratio. So, I mean, this is because this is an example, we can actually, we can write down what they are, right? So I'm just going to write them on the board. So 1 plus square root of 5 over 2, 1 minus square root of 5 over 2. Well, we can see that these are not roots of unity. So it's a non-degenerate sequence. It is a linear recurrence sequence. So I'm making these observations to help us get to the motivation thing. Okay, so it's going to be in the next slide. And then, well, yeah, so it's a linear recurrence sequence. And it is also not a polynomial sequence. And in fact, it is given by this kind of an equation in terms of the roots. So here, this one is alpha 0, and this one is alpha 1. Why? Because alpha 0 is the biggest one, right? I put an ordering on it. So let's keep this a times alpha 0 to the n plus b times alpha 1 to the n in mind, okay? So why do we care continued? Why do we care is going to be related to approximation of algebraic numbers. So in 2023, Yang Guizhou and Koa proved this theorem about approximation of algebraic numbers. And I'm not going to go into technical details, but here, well, we see an approximation, right? And here, well, there's a sequence, which is non-degenerate linear recurrence sequence, which is not a polynomial sequence. So that's why I had this motivating example with the Fibonacci. And what happens is, it's going to be about this d minus 1. So that's why I had this d minus 1 in my examples on purpose. It is the same d minus 1. Because what happens is, when they are proving this theorem, they write un as some combination of alpha I to the n's. It is more complicated. It's not just capital A and capital B. The coefficients will depend on n as well in their case, because they're looking at a more general set of linear recurrence sequences. But looking at it in a more simpler way, we had that example with Fibonacci, and it is the same d minus 1. And whenever you have approximation like this, approximation of algebraic numbers or something else, and then you get a bound, and then, well, the question is this bound optimal, right? So here, could we have something smaller than 1 over d minus 1? So in effect, once we restrict ourselves to looking at that solution set that I presented, which I'll write again.
So the exponent doesn't depend on the degree of the linear recurrence sequence, but just on the degree of psi.
Yes.
So it's true for any linear recurrence sequence.
Yes. Okay, so this was the inequality that we were looking at, right? And I said that, yeah, that d minus 1 is coming from this exponent there. Now let's give this set of solutions a name. Let EKD denote the set of all k tuples C1 to Ck with the Ci is non-negative real numbers satisfying the above inequality. Now the question was that what is the shape of EKD? So we have this theorem. We have, like I said, we have two characterizations. So the first one is that we observe that the solution set EKD is a polytope, and we can give its vertices in an explicit way. So again, here, okay, there are lots of indices, so I'm not going to go into it. But here, this is any of the vertices, and Vj is the coordinates of this one vertex V. And it is sort of given by looking at the power set of the set from 1 to k, and then, well, you look at an ordering, and then actually we are giving these coordinates in terms of the I sub L's. This is an explicit way because, well, you just run through all the subsets in the power set. And then we have the second characterization. It also happens to be the same set of solutions to these 2k many inequalities. And here you can see that, well, K of them are just to say that the CIs are non-negative. And here, even in the first inequality, you see that this is telling us that the sum of the CIs is at most D minus 1. Okay, so before we proceed, I'm just gonna tell you how we get this in terms of the method. So actually, if you look at this, kind of by definition, 2 describes a polytope. It describes a polyhedron, but you can see that it's bounded, so it's going to be a polytope. And then, well, a polytope can be described by its vertices. So to show that 1 and 2 are the same, we show that the vertices satisfy these inequalities. And then, well, that doesn't show anything about EKD yet. To show that, you can show by using the definition of EKD, which we had here, that the vertices are in EKD, and then if you can show that EKD is convex, then you show pretty much everything. So that's how it goes, but yeah, this is too technical, too many inequalities, so let's look at some examples. I just have a small remark that because of this construction, you find the V's by running through the power set. It's a remark that EKD has 2 decay vertices, right? And also, this first characterization gives us an algorithmic way of writing out for listing the vertices. So in fact, you can just write a code by using that characterization that would give you the list of vertices in terms of D given K. So if I just enter K, it can list me all of these things. And you can see here, for K equals 1, there are 2 vertices. So EKD is actually the closed interval 0, D minus 1. And then here, for K equals 2, you're going to have 4 vertices, like 2 to the 2. And it's going to be a trapezoid. And then here, you're going to have 8 vertices. And again, okay, too many numbers. Let's see more concrete examples. So here's the picture. And here, we drew E35. And you can see here that if you just look on the XY plane, right? So this is exactly the closed interval 0, D minus 1. Here is a 4 because D is 5. And then again, if you look at the XY plane, you see the trapezoid here. What does this mean? It means that if you project EKD back to EK minus 1D, they agree, right? It's the same. If you project to the first K minus 1 coordinates. So this whole thing is E35. And you can see that, well, this is a polytope. And then, yeah, so maybe it's a bit hard to see, but here is another trapezoid on the YZ plane. This 202 is still on the wall, but this one is in the air. In case it's hard to see, it's 3D, but it's on a 2D screen. So, and if you project everything down to XY, it will indeed give you E25. And then if you project down to the X axis, it's going to give you E15. So now we see what would happen if you increase or decrease K, fixing D. Now let's look at an image. What would happen if I change D and keep K fixed? But also another point is this 3 is the K, right? It's EKD. It gives you the dimension, right? So you notice that when we're in E15, it says just 1 dimensions and so on. So I didn't try to draw 4 dimensions here. Okay, so if you look at E36, it's going to be this purple one. I don't know if you see it pink or purple, but it is another color. So it is a little bit like, you know, you keep holding on to the origin and you stretch it a little bit. And then the turquoise one is E37. So this is the shape of EKD for certain K and D. And I noticed that, well, our setup was already that we allow K only to be at most D minus 1 anyways. So K will never exceed D. Okay, so it has been some time, so I just want to bring our attention again to the setup. I don't want to keep going back with the button here on the keyboard. We were looking at algebraic integers of degree D, which are Galois conjugates. They are not roots of unity, and we have this order. And this was the first question we looked at, right? The solution set to this inequality with greater or equal to 1. We looked at the shape of it. So the next question is, when do we have the strict inequality? And to get to that, we're going to be looking at when we have equality with 1. And then, well, the last question was, what do we even mean by when? And what I mean is for which k and d. So it is more like, okay, can we put a bound on d in terms of k to get the strict inequality, for example? Okay, so we have this example, so let's reuse it, right? We know the roots. D is here again 2 and k is equal to 1. We already pointed out that we have greater than or equal to 1 all the time anyways. But in fact, with k equals 1, we have equality with 1 on the right-hand side exactly when c is equal to 1. You can actually solve this because we know the roots. And in fact, well, this 1 is d minus 1. And it's not a coincidence. So let's look at another example because we had this polynomial before. I want to see another one, right? So here I increased d, so d is equal to 3 here. And then so this is a polynomial of degree 3. There's going to be, there will be 3 roots. Alpha 0 is the biggest one, alpha 1 and alpha 2 are conjugates. And I'm looking at k equals 1 again. And here we have equality with 1 exactly when c is equal to 2. And here 2 is again d minus 1. Okay, so our theorem is about when we have strict inequality. And if d is strictly greater than 3k, and the k tuple c1 to ck is in ekd, so it already satisfies greater than or equal to 1. But the condition is that d is strictly greater than 3k, then we have the strict inequality in this exponential relation. So the answer to when was that d is strictly greater than 3k. I'm going to stop here. I think I'm out of time. Yeah, so these are the only references I used. So thank you for listening.